January 17, 1945, Luzon Island, Philippines. The air smells of burned metal and jungle rot. In a makeshift laboratory hidden beneath the canopy of mahogany trees, Lieutenant Commander Nakamura Hideaki stands before a workbench cluttered with vacuum tubes, copper wire, and the disassembled components of an American SCR-584 gun-laying radar system. His hands, steady despite 3 nights without sleep, trace the circuit pathways etched into a chassis plate stamped with English words he barely understands. Outside, the distant thunder of American artillery rolls across the mountains like a promise kept too many times. Nakamura's fingers pause over a magnetron cavity, a component so elegantly machined, so impossibly precise, that it seems to belong to a different century entirely. He does not yet know that what he is touching represents not merely a technological gap, but an abyss of industrial capacity, scientific infrastructure, and national will that no amount of Japanese ingenuity can bridge. He does not yet understand that he is holding evidence of his own nation's obsolescence. The radar unit before him was captured 3 weeks earlier during the American landings at Lingayen Gulf. Japanese forces, desperate for any advantage against the overwhelming firepower arrayed against them, had dragged the intact system through 12 miles of jungle to this concealed position. The High Command in Tokyo had issued urgent directives: analyze the enemy's electronic warfare capabilities, replicate what can be replicated, exploit any weakness that might slow the American advance toward the home islands. Nakamura, trained at Tokyo Imperial University in electrical engineering, had been among the finest minds the Imperial Japanese Navy could deploy. He had worked on radar development since 1941, had contributed to the Type 21 air search radar, had believed, truly believed, that Japanese technology, though perhaps smaller in scale, possessed a philosophical purity and efficiency that brute American mass production could never match. Now, as he catalogs each component of the SCR-584, that belief crumbles like wet paper. To understand the profound despair that settles over Nakamura and his team in that jungle laboratory, one must first comprehend what Imperial Japan expected from the war it initiated on December 7, 1941. The Japanese military establishment had studied America carefully, had noted its industrial strength, but had fundamentally misunderstood the nature of that strength. They believed Americans were soft, distracted by material comfort, lacking the spiritual discipline that centuries of Bushido tradition had instilled in Japanese warriors. They believed that American industry, while vast, was oriented toward consumer frivolity: automobiles with chrome trim refrigerators, radios that played jazz music, and that such a nation could not quickly pivot to war production. They believed that a series of swift victories would break American morale, that a democracy of individuals pursuing happiness could never match the collective will of an empire unified under divine imperial authority. Most critically, they believed that Japanese scientific sophistication, particularly in optics and certain specialized fields, would offset American quantitative advantages. These beliefs were not propaganda, not mere wishful thinking. They were articles of faith, embedded in strategic planning, taught at staff colleges, repeated in planning documents that assumed American weakness as foundational truth. The Pacific War's early months seemed to confirm these assumptions. Japanese forces swept through Southeast Asia with a speed that shocked even their own commanders. Hong Kong, Malaya, Singapore, the Dutch East Indies, the Philippines, all fell in a cascade of victories that appeared to validate every premise about Western decadence and Asian martial superiority. Japanese radar technology during this period was adequate, sometimes excellent. The Type 21 radar could detect aircraft at ranges sufficient for defensive operations. Naval fire control systems, while less advanced than British or American equivalents, functioned well enough. There was no sense of technological inferiority, no reason to question the fundamental soundness of Japanese engineering approaches. If American equipment captured during the fall of the Philippines seemed well made, it was dismissed as the product of wasteful over-engineering, typical of a nation that did not understand elegant simplicity. But wars are not won by elegance. They are won by the side that can deliver more shells, more aircraft, more trained personnel, more of everything, faster and more reliably than the enemy can destroy them. And they are won by the side whose technology evolves faster than the enemy can adapt. By 1943, Japanese engineers monitoring Allied radio frequencies began noticing something troubling. American aircraft were evading Japanese night fighters with uncanny precision. American anti-aircraft fire was achieving hit rates that seemed statistically impossible. American naval gunnery was striking targets at ranges and in conditions that should have rendered such accuracy unattainable. The explanation, Japanese intelligence reluctantly concluded, lay in radar technology that had advanced far beyond what Tokyo's laboratories had achieved. Reports filtered back from the Solomon Islands, from New Guinea, from the Marshalls. Descriptions of American radar sets that seemed to operate on principles Japanese scientists barely understood. The High Command issued directives for the capture of intact American radar equipment, but in the chaos of retreat, such captures were rare. Equipment was usually destroyed by withdrawing American forces, or too damaged in combat to be analyzed effectively. The SCR-584 system on Nakamura's workbench represents the first relatively complete American fire control radar to fall into Japanese hands in the Philippines. It is a prize of incalculable intelligence value. It is also a mirror held up to Japanese technological pretensions, and the reflection is devastating. Nakamura begins with what should be the simplest component, the power supply. In Japanese radar systems, power supplies are temperamental, requiring constant adjustment, prone to voltage fluctuations that limit operational reliability. The American unit uses a voltage regulation system so stable, so precisely calibrated, that it seems almost wasteful in its over-engineering. But as Nakamura traces the circuitry, he realizes this is not waste, it is insurance. The system is designed to function flawlessly under conditions of extreme vibration, temperature variation, and electromagnetic interference. It is designed by engineers who assume their equipment will be operated by hastily trained technicians under combat conditions, and who have built in redundancy upon redundancy to ensure that even imperfect operators cannot easily break it. Japanese radar, by contrast, requires skilled technicians, delicate handling, frequent maintenance. The philosophical difference is stark. American equipment is designed for mass production and used by conscripts. Japanese equipment is designed as precision instruments for specialists. The vacuum tubes tell a similar story. Japanese tubes, manufactured with great care in limited quantities, are functional but fragile. The American tubes are mass-produced to tolerances that Japanese factories cannot achieve at scale. More troubling, they are standardized. Each tube fits precisely into its socket, can be replaced in seconds, is interchangeable with tubes manufactured at different factories across the United States. Nakamura has seen Japanese radar systems fail in combat because a single burned-out tube could not be replaced. The spare tubes available were from different production runs, with slightly different dimensions or characteristics, and required hours of adjustment to function properly. The Americans have solved this problem, not through superior individual craftsmanship, but through industrial standardization at a level Japanese industry never attempted. Then Nakamura reaches the magnetron. The cavity magnetron is the heart of microwave radar, the component that generates the high-frequency radio waves that allow precise detection of aircraft and ships. Japanese scientists developed their own magnetron designs, but production was limited, performance was inconsistent, and output power was a fraction of what British and American systems achieved. The British had invented the cavity magnetron in 1940, and had shared the design with the United States as part of the technology exchange that preceded American entry into the war. American industry, applying mass production techniques and precision manufacturing, had turned the magnetron into a component that could be produced by the thousands, with consistent performance characteristics, at steadily decreasing cost. The magnetron before Nakamura is a work of art, but art in the service of mass production. The copper cavities are machined to tolerances measured in thousandths of an inch. The vacuum seal is perfect, capable of maintaining operational integrity for hundreds of hours. The output power is nearly 10 times what Japanese magnetrons achieve. As Nakamura carefully measures each dimension, documents each specification, he is forced to confront an uncomfortable truth. Japan cannot replicate this component. Not because Japanese engineers lack the theoretical knowledge. Nakamura understands the physics perfectly, but because Japanese industry lacks the machine tools, the quality control systems, the trained workforce, the continuous electrical power, the supply of high-purity copper and tungsten, the dozens of supporting industries that American manufacturing infrastructure provides as a matter of course. He writes in his engineering notebook in careful characters, "The enemy's manufacturing precision exceeds our capabilities by a factor we cannot quickly close. To produce 1 unit of equivalent quality would require resources we do not possess. To produce thousands would require an industrial base we do not have. This realization extends beyond the magnetron. The SCR-584's antenna system uses a servo-controlled mount that can track aircraft with mechanical precision, while the entire unit is towed behind a truck on rough roads. The servo mechanisms are powered by components manufactured to standards the Japanese industry reserves for battleship fire control systems, but the Americans are producing these components for a tactical radar set that will be deployed by the hundreds to anti-aircraft batteries throughout the Pacific and European theaters. The computing mechanisms that allow the radar to automatically calculate firing solutions are analog computers of such sophistication that Nakamura initially mistakes them for captured Japanese equipment, assuming no American device could be so cleverly miniaturized. Then he finds the manufacturer's plate. Bell Telephone Laboratories, produced under contract for Western Electric, assembled at a factory in New Jersey that manufactures dozens of these units every day. Every day. Nakamura's team works through the nights, documenting, photographing, sketching circuit diagrams by lamplight while American bombers drone overhead on their way to targets in Manila. They weigh each component, measure each dimension, test each circuit with the limited equipment they have managed to keep functional. A complete technical report is assembled. 50 pages of dense engineering analysis, measurements, component specifications, and theoretical explanations. The report concludes with recommendations. Certain components might be copied using existing Japanese manufacturing techniques. Certain design principles could be adapted to improve existing Japanese radar systems. Certain approaches to circuit design might be incorporated into next-generation equipment. But buried in the appendices, written in language carefully neutral, is the assessment that matters. Full replication of this system is not feasible given current industrial constraints. Partial replication would require diversion of manufacturing capacity currently allocated to other critical systems. Time required for reverse engineering and tooling for production, estimated 18 to 24 months. By which time, enemy technology will have advanced by an equivalent interval. The report is transmitted to Tokyo through the fragile communication networks still connecting the Philippines to the home islands. It arrives at the Navy Technical Research Institute in late February 1945, where it joins a growing stack of similar reports from engineers scattered across the collapsing perimeter of Japan's Pacific Empire. Reports describing American proximity-fused anti-aircraft shells that explode automatically when near an aircraft, eliminating the need for precise altitude fuses. Reports describing American fighter aircraft with radar sets small enough to fit in a single-seat fighter, allowing night interception without ground control. Reports describing American bomber navigation systems that allow precise targeting through cloud cover, turning weather from a defender's advantage into irrelevance. Reports describing American aircraft production figures, thousands of heavy bombers per month, production lines so efficient that the cost per aircraft is steadily declining even as performance improves. The engineers in Tokyo read these reports with a growing sense of doom that they cannot express in official communications. They have known since Midway that the war is unwinnable in any conventional sense. But there had been hope. Irrational perhaps, but hope nonetheless, that Japanese technological sophistication might provide some advantage, some asymmetry that could be exploited. The radar reports extinguish even this hope. American technology is not merely equivalent to Japanese technology. It is comprehensively superior, and the gap is widening. What Japanese engineers expected from America was quantity without quality, mass production without precision, industrial might without scientific sophistication. What they discovered was a nation that had solved the problem of producing precision equipment at mass production scale, that had married scientific research to industrial capacity in ways that Japanese planners had never imagined possible. They discovered that American universities were training engineers by the tens of thousands annually, that American industrial laboratories employed more research scientists than existed in the entirety of Japan, that American factories operated with electrical power availability and raw material supplies that Japanese planners could only fantasize about. They discovered that the Manhattan Project, still unknown to Japanese intelligence in early 1945, was merely the most spectacular example of America's ability to mobilize scientific talent and industrial resources toward a single objective. In the cramped offices of the Navy Technical Research Institute, senior engineers hold quiet conversations that would be treasonous if reported to military intelligence. They speak of the American industrial system as one might speak of a force of nature, not an enemy to be defeated, but a reality to be acknowledged. One engineer, Yoshida Takeo, a specialist in radio frequency design who had studied at MIT in the 1930s, tries to explain to his colleagues what they are facing. In America, he says, there are more machine tools in a single automobile factory than exist in all of Japan's aircraft industry. Their telephone system has more vacuum tubes in continuous operation than we have manufactured in total since the war began. They produce more electrical power in 1 month than we produce in a year. This is not a question of courage or spirit. This is arithmetic. But arithmetic, no matter how devastating, cannot be spoken aloud in an empire sustained by mythology. The official position remains that Japanese technological development continues, that new weapons are being prepared, that the homeland's defenses are impregnable. The engineers maintain silence, continue their work, and watch the maps as the red lines marking American advances creep steadily closer to the Japanese home islands. Nakamura never sees his report's impact. His position in Luzon is overrun by American forces in March 1945. The laboratory, the captured radar, his meticulously documented analysis, all are lost when Japanese forces retreat further into the mountains. He survives the war, returns to a Japan that no longer exists in any form he recognizes, and spends the rest of his career teaching electrical engineering at a small technical college. He never speaks publicly about his work during the war, but in the notebooks he keeps in retirement, there are repeated sketches of that magnetron cavity, drawn from memory with obsessive precision, as if by understanding its geometry he might finally understand the gulf between what Japan aspired to be and what it actually was. The symbolic weight of that magnetron, a hollow cavity of machined copper, empty space shaped to channel electromagnetic energy, becomes in Nakamura's private mythology the emblem of Japanese wartime self-deception. It represented power generated not from spirit or will, but from industrial processes so complex, so dependent on supporting infrastructure, that they could not be replicated by determination alone. It represented a cavity, an emptiness at the heart of Japan's strategic planning, the assumption that fighting spirit could substitute for factory capacity, that racial purity could compensate for technological inferiority, that an empire built on conquered territories could match a continental industrial power with unlimited resources. Other symbols emerge from similar encounters. Japanese pilots who are shot down and captured describe their shock at the abundance of American equipment, the casual waste that seems to characterize American logistics. One pilot, interrogated after being rescued from the ocean near Saipan, describes watching American construction battalions bulldoze a jungle and construct an airfield in a matter of days, using machinery in such quantities that vehicles were simply abandoned when they broke down, rather than repaired. He had been trained to treat his aircraft as a sacred instrument, to husband every drop of fuel to make each bullet count. The Americans treated aircraft as expendable commodities, flew training missions that consumed more fuel than Japanese squadrons received in a month, practiced gunnery with ammunition allocations that Japanese pilots would consider sufficient for months of combat operations. A Japanese submarine officer, captured when his vessel is sunk off the Philippines, is brought aboard an American destroyer for interrogation. What breaks his spirit is not the interrogation itself, which is conducted correctly under the rules of war, but the casual comfort of his confinement. He is given soap, actual soap, not the rice bran substitute Japanese sailors have used for 2 years. He is given coffee with sugar, bread with butter, a bunk with clean sheets. The destroyer's mess hall serves meals that would be considered luxurious in Japan's officer clubs. He realizes that this is not a special occasion, not a meal prepared to impress prisoners. This is simply how American sailors eat, routinely, every day, on a small destroyer thousands of miles from home. The abundance is not propaganda. It is simply reality. This abundance extends to technology in ways that Japanese engineers find almost incomprehensible. American factories produce radar sets in such quantities that they can afford to assign them to individual aircraft, to small patrol boats, to forward observation posts. Japanese radar, by contrast, is concentrated at critical facilities, is maintained by specialists, is treated as a precious resource to be carefully husbanded. The philosophical difference is profound. Americans use technology to reduce the skill requirements for personnel, to allow average soldiers and sailors to perform tasks that Japanese doctrine reserves for specialists. This is not because Americans are less capable. Captured technical manuals reveal training programs of considerable sophistication, but because American doctrine assumes that equipment will be available in sufficient quantities to distribute widely. The submarine officer, in his debriefing after repatriation in 1946, tries to explain this to Japanese naval historians compiling records of the war. "We were fighting different wars," he says. "We were fighting a war of scarcity, where every resource must be carefully allocated, where every loss is irreplaceable. They were fighting a war of abundance, where loss is acceptable because replacement is assumed. Our sailors were brave, their sailors were brave. But our sailors were sailing in submarines that could not be replaced, carrying torpedoes that often did not function properly, trained on equipment we could not afford to use for realistic practice. Their sailors were sailing in submarines that were being launched faster than we could sink them, carrying torpedoes that worked, trained on shore-based facilities that used actual torpedoes for practice runs. Courage cannot compensate for such disparity." By the spring of 1945, these disparities are visible in every dimension of the Pacific War. American forces conduct amphibious assaults with preliminary bombardments that use more ammunition in a single day than Japanese factories produce in a month. American aircraft conduct raids with formations of hundreds of bombers, protected by fighters whose performance characteristics Japanese aircraft can no longer match. American submarines operate with impunity in waters that Japan can no longer patrol effectively, sinking merchant vessels faster than Japanese shipyards can replace them, cutting the maritime supply lines that the empire requires to survive. Japanese radar operators, tracking American raids with the increasingly obsolete equipment they are forced to use, watch their screens with a sense of futility. They can detect the raids barely, but Japanese fighters can no longer climb fast enough to intercept before the bombs fall. Japanese anti-aircraft batteries, firing shells with mechanical fuses, achieve hit rates so low that they are essentially irrelevant. The gap between detection and effective response widens until detection itself becomes merely a way of knowing, with precision, the moment of one's own destruction. In the final months of the war, Japanese engineers are ordered to prepare defensive systems for the expected American invasion of the home islands. Plans are drawn for radar networks, for coordinated fire control, for electronic warfare measures that might disrupt American communications. The engineers comply, produce detailed specifications, submit requisitions for components and materials, but in private conversations, they acknowledge what cannot be stated in official documents: that Japan no longer possesses the industrial capacity to manufacture the required equipment, that even if equipment could be manufactured, it could not be powered reliably given the collapse of the electrical grid, that even if it could be powered, the operators who might use it effectively are either dead or lack the training time that effective operation requires. The war ends before these plans can be tested. When American occupation forces arrive in Japan, they conduct comprehensive surveys of Japanese scientific and industrial facilities. American intelligence officers, many of them engineers and scientists in civilian life, tour Japanese radar laboratories with a mixture of professional curiosity and pity. The equipment they find is ingenious in design, showing real scientific sophistication, but primitive in manufacturing quality. Components that American factories produce automatically are assembled by hand in Japan, each unit slightly different from the last, each requiring individual adjustment. Research facilities that in America would house hundreds of scientists have staffs of dozens, working with equipment that is obsolete by American standards but represents the best Japan can produce. The technical reports prepared by American survey teams make for melancholy reading. They document a nation that understood modern science, that possessed talented engineers and researchers, but that lacked the industrial infrastructure to translate knowledge into power. Japanese universities had produced theoretical work of genuine value in fields ranging from quantum mechanics to material science. But the pathway from theoretical knowledge to practical application, the complex infrastructure of industrial research, pilot production, manufacturing scale-up, quality control, logistics, this pathway was narrow and fragile in Japan, could not support the mass production of sophisticated technology that modern warfare required. One American engineer, surveying a Japanese radar research facility in the suburbs of Tokyo, writes in his report, "The scientists here are competent, in some cases brilliant. Given adequate resources, they might have developed systems comparable to ours. But they were never given adequate resources. They were asked to compete with American industry using tools that American industry discarded a decade ago. The wonder is not that they failed, but that they accomplished as much as they did." This assessment, clinical and almost kind, nevertheless confirms what Nakamura understood when he examined that magnetron cavity in the Philippine jungle, that the war Japan had chosen to fight was unwinnable, not because of any failure of courage or spirit, but because modern war is fundamentally industrial, and Japan had challenged an industrial power whose capacity exceeded Japan's by orders of magnitude. The magnetron, that hollow cavity of precisely machined copper, becomes in retrospect a perfect symbol for the hollowness of Japan's wartime ideology. The militarists had promised that spiritual purity and martial discipline could overcome material disadvantage. They had promised that Japanese technology, though perhaps smaller in scale, possessed qualities that crude American mass production could never match. They had promised that the Americans, distracted by democracy and comfort, would lack the will to fight a determined enemy. Every promise was hollow. Spirit could not machine copper to thousandths of an inch precision. Discipline could not generate electrical power from force of will. Determination could not build machine tools that Japan's industrial base could not produce. The engineers who survived the war carry this knowledge with them into Japan's post-war reconstruction. Many of them apply the lessons learned in painful ways during the war. Lessons about manufacturing precision, about standardization, about quality control, about the integration of research and production. The Japanese electronics industry that rises from the ashes of defeat is built partly on these lessons, on a hard-won understanding of what industrial sophistication actually requires. There is bitter irony in the fact that Japan's post-war economic miracle is built partly on knowledge gained through wartime failure. That Sony and Panasonic and Honda emerged from a generation of engineers who learned, by studying captured American equipment in jungle laboratories, what excellence actually looks like when divorced from mythology. But in 1945, in the final months before surrender, Japanese engineers have no vision of future success. They have only the evidence before them. The radar sets they cannot replicate, the aircraft they cannot match, the bombs falling on cities they cannot defend. They have only the knowledge that the war Japan chose to fight was lost before it began. Lost in the moment when planners in Tokyo confused their own wishful thinking with strategic reality. Lost when they assumed that an island nation with limited resources could defeat a continental power whose industrial capacity was essentially unlimited. In his retirement, Nakamura sometimes thinks about alternate histories, about what might have happened if Japan had understood in 1941 what he understood in 1945. But such speculation is pointless. The understanding came from the experience, could not have preceded it. Japan's leaders made the choices they made based on the information they believed, the ideology they embraced, the strategic culture that shaped their worldview. The radar set on Nakamura's workbench did not change the outcome of the war. That outcome was determined by industrial capacities set in motion long before Pearl Harbor. What it changed was Nakamura's understanding, and in changing that understanding it became a teacher more effective than any defeat in battle could have been. The lesson was simple and absolute, that modern war is not a contest of wills but a contest of systems. The side with the better system, the system that can produce more equipment, train more personnel, absorb more losses, innovate more rapidly, project power more effectively, that side wins. Courage matters, strategy matters, tactical brilliance matters, But when the gap in systematic capacity becomes large enough, these qualities become irrelevant. Japan fought with courage that deserved a better cause and a wiser strategy. But Japan fought without the industrial system that modern war requires. And so Japan lost as thoroughly as any nation has ever lost, learned in the hardest way possible that mythology cannot substitute for manufacturing, that spirit cannot replace steel. The cavity magnetron sits now in a museum, a trophy carried home by an American soldier who found it among the ruins of Manila. It is labeled simply as a component from a captured American radar set, evidence of Japanese technical intelligence efforts. Visitors walk past it without recognition, do not understand what it represents. But for those who know its history, it remains what Nakamura understood it to be: a hollow space precisely shaped that focused energy with devastating effectiveness. A symbol of power that cannot be wished into existence but must be built, patiently and systematically, by nations that understand that war in the modern age is fundamentally a question of capacity. And a reminder that the most dangerous illusion a nation can embrace is the belief that will alone can compensate for the hard realities of industrial mathematics. In the end, Japanese engineers copied American radar, and in copying it, learned what they should have understood before the war began: that they were already defeated, not by American radar, but by the system that produced it, a system Japan could never match, could never overcome, and should never have challenged. The war had left them behind long before they realized they were falling.